Hello everyone, my name is Xin Qi from the University of Science and Technology of China. Here I'm going to represent my paper Joint Network Selection and Task Offloading in Mobile Edge Computing. This report is divided into 4 parts. The first part is about the introduction. As we know, the Internet of Things has been driving the development of many computation-intensive and delay-sensitive applications, such as augmented reality and connected cars. However, the computation capability of users are not sufficient to meet the delay and computation requirements of these applications. A common solution is uploading those tasks to the remote cloud through access points or base stations. But there are two major disadvantages of the cloud computing. First, long transmission distance and expensive bandwidth will lead to great transmission delay, and cloud computing is unable to satisfy the requirements of delay-sensitive applications. Second, data is the foundation of an application, while the growth of the data generated on the IoT devices make it impractical to transmit the data to the remote cloud for the privacy and storage reasons. To fulfill the requirements of such tasks, mobile edge computing is proposed. However, due to the constraint of the resources, it is no trivial to preserve the satisfactory quality of service for user tasks. This is mainly because the reasons of edge servers are not as abundant as those of the centralized clouds. What's more, the density of the base stations has been increasing and is expected to reach up 50 per square kilometers in future 5G developments. And the network selection of users will directly affect the quality of the mobile edge computing system. To illustrate the importance of the network selection, we consider a typical mobile edge computing scenario with 4 base stations. In general, users tend to access the base station which is closest to it, like 1 and 3. While as shown in the figure, base station 1 and 3 have long queues to process. It will lead to a long computation delay. Consider this situation in the figure. It is better to select the number 4 base station. Therefore, in order to improve quality of service of a mobile edge computing system, operators must jointly optimize the network selection and task offloading strategies of users to achieve the optimization of the whole system. Consider a typical mobile edge computing system. We use M and N to represent the base station set and the user set respectively. And we also use XIJT and YIJT to represent the network selection strategy and task offloading strategy. Hence, the whole processing delay consists of 3 parts: local delay, transmission delay, and remote delay. Each of them can be calculated as follows. The goal of our problem is to minimize the whole processing delay in given time span. Hence, we can formalize the network selection and task offloading optimization problems as follows. A major challenge of directly solving our problem is that the long-term reason constraint of base station, coupled with the network selection and task offloading. So, to address this difficult problem, we divide the overall processing delay into two parts: user side latency and edge side latency. User side latency consists of the local delay and transmission delay, which only rely on on the user own decision. Edge side is the remote delay. The core of our algorithm is to the core of our algorithm is to tolerate as much user side latency as possible, as shown in the figures. In our online algorithm, we first initialize network selection and task offloading decision vectors randomly. Then, at each time slot, we can compute each delay items. After that, our algorithm makes appropriate decisions about network selection and task offloading by the following strategies. Let T hat be the last network switching time slot over the past time, and we calculate the total edge side latency in the time slot T hat to the T. Our algorithm checks whether the edge side latency is at least row times than the user side time. If so, it is shows that there is series congestion at edge side, and we have to recalculate the new decision vectors. The positive parameter rho is used to adjust the frequency of network switching. Large rho means that we can tolerate more edge side latency in our more edge side latency. For different type of applications, we can set different rho values to get satisfactory quality of service. To show the performance of our online algorithm, we carry out extensive simulation driven by the real-world trace. The total simulation area is divided into 9 square cell grids. Each of them has deployed a base station. The first set of experiments, we measure the average delay of users in 20 time slots, and the duration of each time slot is set to 30 seconds. We can see from the first figure when the number of users spans a range of values starting from 20 to 200 to 300. Our algorithm has a clear advantage over the other two benchmarks. For example, when the number of users comes to 300, our algorithm improves performance by 25% and 34%. Next, we take a closer looking into the different type of delays. Unlike the total delay, different type of delays is a key metric to evaluate the performance of the entire system. In this test, we evaluate 3 different types of delays by setting the number of users to 300. From the picture, LD, TD, and ED are abbreviated forms of local delay, transmission delay, and edge delay, respectively. It can be observed that our algorithm has an advantage over the two benchmarks, regardless of any type of delays. Finally, we explore the computation resource utilization of each base station when the three algorithms are used. From the picture, our online algorithm achieves stable and efficient resource utilization on each base station. In this paper, we studied the problem on joint network selection and task offloading in mobile edge computing networks to reduce the computation delay and transmission delay. Using querying theory, we established a best framework of the problem on the multi-dimension resource constraint. Then we formulate the joint optimization problem as a long-term problem and decomposed it into a series of one-shot problems. Extensive trace-driven simulations show that the proposed online algorithm is computationally efficient and can significantly improve the system performance. This is all my reports. Thank you for your listening.